All right, welcome back to the second segment of the Destroying Array module. Remember that in this part, we only discussed the implementation. So this will make a lot more sense if you watched the previous part first. So if you haven't done that, please go back and take a look at that video where we actually go over the problem statement and the main ideas for a solution. And it's that solution that we are going to try and implement now. So let's get started here. As usual, you can find a link to the problem itself in the description of this video, so you may want to cross-refer that to make sure that the input-output formats are as you expect and so on. So the first part in the main function is going to be the usual. I think this is fairly standard parsing of the input. We're going to first take in the number of elements in the array, and then we're going to store the elements of the array in a vector of integers. We're also going to have a state vector which tells us which locations are currently occupied and which locations are currently empty. So this state vector will evolve as we go through the process of adding elements to the array one by one. Then we declare again vector of integers to take in the sequence in which the destruction happens, and then we just take in all of these inputs. So let me just also point out the limits. I believe the value of n ranges from 1 to 100,000, and the values of the elements in the array would range between 1 and 10 to the 9. So all of this would fit within the integer data type, and that's why everything that you see here has been declared as an integer, except for the index variable in the first for loop, which I think is just really not intentional. So that could have very easily also been an integer, and that's not really going to be a problem. But remember that we are tracking the sums of elements of segments in this array. So when you add up these large numbers, then you might overshoot what can be stored in an integer data type. So when we declare variables that are going to store the answers for us, at that point we switch over to the long data type, which can handle the larger numbers that we are going to need as we go along. So after taking in all of the input, we declare, we instantiate the disjoint set union data structure. Again, I do this with n+1 elements so that I can simply talk about the ith element without having to adjust for indexing to go back and forth between 0-based and 1-based indexing. You might have a different taste with regards to this, but if you do it differently in the sense that you initialize it with n elements, then please remember to adjust your indices properly, because the input sequence is a permutation of 1 to n. So you will have to roll it back by 1 if your elements are ranging from 0 to n-1. All right, the first thing that we do is to, of course, reverse the sequence of instructions, and we are going to declare a vector of long integers to store the answers that we're supposed to output at the end. And we're going to use the variable current answer to keep track of the answer in the current stage of the process. So now let's move to what is really the heart of the whole algorithm. So this is where we actually go through the process. So we're going to go over the sequence, and then we're going to do the union operations based on the situations that we have already discussed in the previous video. So first of all, when we say that the exit element is now being added, we modify the state of the exit location to 1 to indicate that this location is now occupied, and now we create the singleton set that is associated with this location. Now normally make set would just take one parameter as input, and it would say, okay, I want to create the singleton set involving the ith element, and that would have been enough. But remember that we are tracking the sums of the elements, the actual numbers that are sitting at these locations. So we're going to use the indices to keep track of how the sets are evolving, but we also need to keep track of the numbers that are involved at these locations. So I'm also passing that as a parameter, and what will happen is that that's going to be used to initialize the value of some set, the sum of the elements in the set. We're going to store that in a separate array, and for the singleton set, that's just going to be the value of array of x. It's just going to be that number. So we pass that in as a parameter as well so that we can track this value. Now we need to look at whether the introduction of the element at the xth location is causing any merges or any extensions of previously existing sets. So that's exactly what we are doing here. We are checking if the left neighbor is non-empty. If yes, then we take a union between x minus 1 and x. And if the right neighbor is non-empty, then we take a union between x and x plus 1. So this non-emptiness is essentially checked by the value in the state array. And notice that the first part of that if clause is just safeguarding us from falling off the cliff, so to speak. So that accounts for the edge cases that I was mentioning briefly in the previous video. So of course, if x is 0, then x minus 1 will not make sense. And if x is n, then x plus 1 will not make sense. So that's essentially what we are trying to be careful about here. And now that we have done the merging, let's think about what should be the value of the answer at this stage. Remember that we want to return the weight of the heaviest chunk, and we know the weight of the heaviest chunk from the situation when this element had not yet come into the picture. So we know the heaviest chunk from the previous iteration in the sequence. Of course, if we are just at the beginning, then current answer is initialized to 0, and we really have nothing to check. We just output the value of the singleton chunk that got introduced. So just as a sanity check, that's what happens at the very first step. But in a general iteration, the value of the variable current answer gives us information about the heaviest chunk in the previous snapshot. And now there was this one element that came in, and it potentially merged some sets, or it potentially manifested as a singleton set. But essentially, the only new contender is going to be the set that this new element belongs to. All other sets are pretty much they remain the same. They have the same weight as from the previous step. And of course, some sets disappeared. And notice that if one of the sets that disappeared was actually the champion set from the previous iteration, then it's going to at least retain that status when it gets merged with the new element. So the only reason a set disappears from the previous snapshot is because the set got enhanced with the new element that was added. So it got merged with one or two sets depending on the situation that you are in. So notice that the value of the set, the weight of the set only gets better because all of the numbers in the array are non-negative. So we don't have to worry about, if we lost this set, maybe the maximum is the crown now needs to shift to one of the other sets, and we need to loop through all of the other sets and check if one of them got better. Notice that if the newly introduced element could have been potentially a large negative value, then this would have been a problem. Then we would have to worry about, well, after this merger, maybe there was a set that was doing very well and was championing the previous round, and now it just became much worse and we need to find a new champion. But notice that this is something we don't need to worry about at all because all the elements have non-negative values. So when you bring them in, the previous sets, if at all, they get better. So all that we need to do is check if the new set that came into the picture, which could either be a singleton or it could be the merger of some sets from the previous iteration, we just need to sanity check the weight of this set against the best value that we had from the previous iteration. So if the weight of this newly created set dominates current answer, then we need to update the value of current answer. Otherwise, we leave current answer as it was. So that's essentially what is happening in the penultimate line of this code snippet. And after this, we basically just do the formalities. The logistics would be to push the value of current answer into our answers array so that we are tracking the answers at every iteration. And once once you have gone through the whole process, we need to shave off the last answer that we add to the answers array. And the reason for that is at the very end, when you add the last element to the array, you have reconstructed the whole array, and the answer that you get at that point is going to be the sum of all the elements in the array, and there's just one chunk. But if you look at the output that you're supposed to produce, your output only starts from the heaviest chunks after the first element has been removed. So this last thing that you add to the answers array, that's not really relevant, so we want to get rid of it. That's the pop operation that you see here. And after this, your answers array is ready for output. Do remember to reverse the answers array, because we have been collecting the answers in the opposite order of what actually transpired. So we need to reverse this back so that the output is consistent with what is expected. So at this point, we are pretty much done. Let me just quickly recap a couple of small changes that we needed to make to the union find class. I'll not recap the whole class because that's been described in some detail in the previous module, so do check that out if you haven't already. But one function that we did need to add here was the make set operation. And even before this, I will mention that you have to adjust your initializations a little bit. So in the previous constructor, the whole thing was set up to capture the state of n singleton sets. So we wanted every element to be its own set. But now what we do instead is we lay the groundwork, we create enough room for n sets to be, or n elements to be eventually added, but initially all the sets are empty. So all the parent pointers pointing to -1, it's, you know, some value to say that these are not yet defined. The depths of the trees are also -1, just to say that these trees don't exist, and, you know, things like that. So we made some adjustments to how the constructor works, and make set is what captures the creation of singleton sets as they come along. So of course there are multiple ways in which you could do this. I chose this because it felt natural to me in terms of just being reflective of the process as we described it, but I'm sure there are other equally valid implementation strategies. So although I'm not showing you the modified constructor here, you can find the entire code as usual in the official repository. And let's just quickly look at what's happening in make set. So when you're creating the ith element, as usual, the ith element at this point being a singleton set is its own leader. So the parent simply points to itself, and this is a tree which has just one root. So by convention, its depth or rank is going to be 0. It's a set whose size is just 1. It's a singleton element. And of course, when we create a new set, we increase the number of sets. So we increment the numsets variable accordingly. And notice that the extra thing that we are tracking in this problem is the sum of the elements in any given set. So the sum set array at the location I needs to be updated so that it has the value of the element in the array that we were working with. So remember, we passed this as a parameter. That's the second parameter here. So some set of I is initialized to x. And again, one thing that I'm not showing you that is actually quite important is that when you're doing the union operation, you do need to update some set there as well. So some set of y will become some set of y plus some set of x. So basically, you want to bring in the sum of all the elements that were there in the set being tracked by x to now the larger set that is being tracked by y. So this is very similar to the updates that we did for tracking the minimum element, the maximum element, the number of elements in the sets, the sizes of the individual sets and things like that. It's very much in that spirit. So I hope that you'll be able to work through this yourself, and just in case you need to cross-check or you need to refer to it, the entire code is available in the GitHub repository, so you're welcome to take a look at that as well. All right, so with that, we come to an end of the description of how we would solve destroying array. And I hope you enjoyed this. Let me know what you think in the comments, or keep the conversation going on Discord. I look forward to seeing you there. And we will be discussing one more problem in this week. So I will also see you in the next video. Thanks for watching, and bye for now.